All right.
All right.
Recording?
Thanks.
Yeah.
So excited. Happy Photon Day. It's gorgeous out. I'm glad we're gonna get out on the water today. So it's a perfect day for what I'm gonna talk about. So what we just heard yesterday on the modeling you did was remote sensing reflectance, but it was based on a model to get at and derive the components of B and A to do that remote sensing reflectance. So what we talked about yesterday again is the different radiance or radiance measurements. So today we're going to go over how you actually make the remote sensing reflectance measurements using radiance and irradiance. And that's important. I'll get to in a minute because it really does relate to exactly what the satellite is seeing. So that's what the sort of the prelude of the two talks today. I'm going to go over what are the AOPs, the apparent optical properties, how do we derive them, why are they important? Next slide already. Some examples of what the AOPs look like, and then we're going to jump into another set of AOPs called reflectance measurements, remote sensing reflectance being one of them. And why they're really important. And then we're going to talk a little bit about the sources of uncertainty. So hopefully we'll go over some of the theory, we'll go over the background, the derivations. I'll give you a bunch of examples of way to do reflectance measurements in the ocean, three of which you'll see today in the lab. So stop at any time. Hopefully this is a little bit of shorter lecture than yesterday I gave. It's got almost half the number of slides. So apparent optical properties. The AOPs are usually, as you'll see, the ratios or as in reflectances or their depth derivatives of radiometric principles. So you saw that yesterday a little bit, just taking a depth derivative of different radiometric properties is a way to understand what's going on in terms of the light field change underwater. What we like to, why do we use AOPs? Because we want a good AOP that weakly depends on the external environment, cloud conditions, those kinds of things, the sky angle, the sun zenith angle, or sun zenith angle, surface waves. And so I'm going to point this out. If there's another beautiful sunny day, somewhere between 8:30 and 9, I want you to look up right about here. You seen that?
Yeah.
Do you know what that is?
Das Glint, Sunglint.
But what's causing those high frequency patterns that you've seen?
Yeah.
There's these light and dark patterns.
See the ripples on the water?
Correct.
So
So that's surface reflectance off the water. We'll get to that. And you'll see what the impact is in terms of trying to make those measurements when you have these troughs and crests of the water and light coming at a shallow angle or a low angle sun angle. You'll see that it's creating these patterns of light and dark just based on the reflectance. If it was a planar surface, it would just be a bright spot. All same color, same intensity. But those wave patterns are what's shifting the light field. Very high frequency pattern, creating these light spots, very bright spots, very dark spots. Okay, so that's just a little intro to remember your boundary effects. What's happening, as we saw today, the bottom boundary, air sea surface boundary. So why did IAOPs kind of start getting measured some 40 years ago, really? Because IOPs are really hard to measure in an environment. You can measure them on a benchtop, you could do all that easily. But if you've ever used a benchtop spectrophotometer, that's what an ACS is, just compacting that all into an underwater sensor that you can deploy. So they were really hard to do a long time ago. The light field measurements created much longer ago, were much easier to measure, but were very difficult to interpret. We'll get to that in a minute. So that's why IAOPs came about and why they're important. So first off, this is sort of a question point more than anything, is irradiance and AOP. It's not an AOP, it is the actual fundamental property of light measurement. So, and why is that? There's two different cases, clear water case, stuff in the water case, as you said today, you know, in doing all this modeling. Not a whole lot of particles, not a whole lot of CDOM, some particles, some CDOM. So if you just look at the upwelled irradiance, that's one of the measurements. So you're looking at the amount of light coming out of the ocean. You can see depth variations. You can see different sky variations in these two examples. So while the irradiances do depend on the radiance and somewhat on the IOPs, but they more importantly, they strongly also depend on the incident lighting conditions. How bright is the light? Is the atmosphere diffuse? Is it cloudy? So that's what makes them very difficult to use as a direct correlation to the IOPs. We have to derive some other principles, the AOPs, in order to have a more exacting relationship to the AOPs, IOPs. So irradiances are definitely not an AOP. So let's just talk about diffuse attenuation coefficients of irradiance, or just more in general, K functions. So we went over all these types of stuff. You've got upwelled radiance, you can measure downwelled radiance, you can measure irradiance, downwell and upwell, you can measure scalar radiance, you can measure PAR. You can derive Ks from all those different measurements. So there's a lot of ways to get at a K measurement. I'll just describe that a little bit more, how we calculate Ks, but I think you've already seen hints to it. Cat's talk yesterday. Derivatives, derivatives, derivatives. So again, K functions are really strong contenders for an AOP. Again, an AOP is we want it to be an apparent measurement of the optical properties of the water. Not an inherent one, which means they're directly related to the inherent properties. This is an apparent property that looks like it should look like something like the IOPs. So again, derivatives. There's the derivative. We're looking for the change in the light field, change in the irradiance, in this case, the downwell irradiance. So we take the derivative. If we've got a profile, we've got some measurements, step measurements, we take that derivative of the irradiance over depth. We do have to normalize it by the light at some point in the depth, so that we're, you know, accounting for the change also in light. That's the KD value. More importantly, this is really the easy definition. 1 over the depth where you're making the measurement is the natural log of the irradiance right below the surface, downwell irradiance right below the surface, divided by the irradiance at some depth, over the depth of which you're trying to calculate that diffuse attenuation coefficient. So so here we have depth profile. Here we have different values of the irradiance. We can say it's downwelling or upwelling irradiance. And here we have a bunch of different sky conditions. So you're just plotting an irradiance downwell irradiance profile. You can see the depth it attenuates, right? Pretty simple. Looks pretty flat. Looks pretty constant over this. So that is intuitively, you can say, okay, I know something about how the light is attenuating. And if it looks pretty constant with depth, or it's just linear with depth, I should say, slightly nonlinear with depth, then you say, okay, I know what I can generalize what the attenuation coefficient should be. Okay. Here we go again, just trying to reiterate. We want an apparent optical property, K, because we want a strong relationship to the IOPs and less on the external incident light field. So again, we go back to this clear water case, stuff in the lake. In this case, it's reservoir, Crater Lake versus San Vicente, stuff in the water. There's the wavelengths. This could be KD or KU. KD, KU on the y-axis. Here's the KU for pure water. Should be pretty constant. Not really changing the water in terms of its concentration or raising in the water. But let's just focus on the red line, which is the KD over an interval of 5 meters to 25 meters depth. So this is the spectral KD. So you see that, at the surface, the KDs are very small. I'm sorry, no, at the surface at the blue wavelengths, the KDs are very small, and then you go out into the red. So in this case, it's pure water, pretty much. It's clear water. So you'd expect the attenuation coefficients to generally kind of match A. Here in the more stuff in the water case, now we've got really strong KDs in blue, peaking back up again in the red. Some moderate kind of stuff in the water case. What does this KD in the red spectrum look like? Again, we just went through all this modeling. This spectrum kind of familiar to you. The absorption spectrum, again, it's very similar to the absorption spectrum. Not an exact match, but it's very similar to it. The point here I'm trying to drive home is we want to drive these variables called the apparent optical properties that have the most dependent on the IOPs of the water. All right, so now we know how to, with the example of KD, the diffuse attenuation is the radiance attenuation, and how to calculate that. So what happens with depth? How does KD change with depth? The deeper you go, the deeper you go. So there's a point at which you can see here, there's a diffuse attenuation coefficient, depth, whole bunch of hydrolyte parameters. In this case, you can see it's pretty clear water. So what happens here down here? You get a convergence. Basically, we get a convergence called the asymptotic light field. So at depth and far away from the bottom, the radiance is no longer affected by the boundary conditions. And also what happens in the water down there, even in clear water cases, you get to a point to where the optical properties really aren't changing anymore. And they're all converging spectrally down to one constant value. That's the asymptotic light field. So if you remember the plots I did yesterday, those big circle plots for the fisheye lands, you didn't quite get to the asymptotic light field, but you could start to generalize it and see that deeper and deeper you go, the more flat and planar and consistent those little depth slices of the irradiance distribution, the radiance distribution stayed the same. So for a given water body, the K's all approach the same value. The deeper you go, that's the asymptotic diffuse attenuation coefficient, K infinity, which is an IOP, or at least solely depends on the IOP. So once you hit that asymptotic light field, there's a more direct relationship now to the IOPs. But even in these shallower waters, there's still a very good dependence on the IOPs, but you're still slightly conditioned by the light field. So how do we measure this? In theory, like I said, you take some depth intervals and you calculate the derivative over those two different depth intervals. You normalize it by usually just below the surface, in this case of the irradiance, so you get a normalization of that. So then you can drive, if you know the KD, really great thing is you can also just create now a profile of what the irradiance distribution looks like, because now you know how irradiance is attenuated with depth. So that's the equation. DD is equal to whatever is hitting the surface or just below the surface coming from the sun and the sky. That's e to the integral of the KD over depth, some depth. All right, so now back to, I wish I would have just off in about an hour in my talk. So here's what that profile would look like. underwater in a wavy surface. That's what we talked about, the reflection patterns here. That's a reflection impartation, but some of that water, some of that light is going to go through that surface, air sea surface, and go into the water. So you also have the impartation of wave focusing effects. When you look up, diving down, you're looking straight up, you can still see those patterns because now the light bouncing through those waves, crests, hitting them at different angles. So the angle of an incidence is just varying very greatly. And so you see these bright and dark patterns again. So when you're doing a profiling instrument, and today we'll do some, it's really important to always understand and see what the sea surface state is. Big swells, other small swells, there's a lot of ripple going on. So important when you make these measurements and you're out in the field, record that as part of your data, even if it's just an eyeball. It's better than nothing, so you can do a later interpretation of the actual measurements profiling. Always important, capture the boundary effects. That's why it's also important when you're doing these measurements to look up in the sky, or even better, take a picture of the sky as best as you can to say, was it clear like today? Or yesterday when we had patchy clouds, was it patchy clouds? So that's what all this is about. It's not only wave focusing, but as you're doing this profiling, it's dropping. What happens if the cloud goes by? Your intensity is going to change a lot, obviously. That's why it gets grayer when we're outside of the clouds.
I just wanted to add, so when you become big scientists and stuff, and start studying this kind of data to us, to see that. Ask them, you will ask for a photo.
Yes.
Exactly what you just said.
Yep.
Just to allow us to understand that this, it's, especially now it's self-legislation.
Yep. One of the systems that you'll see today, actually, it's not attached, we didn't bring it, but it has a GoPro camera on it, so it's always capturing an image of the sky as we're going along and making these measurements. Yeah, go ahead.
What do you have the homogeneous but still cloudy sky, like if the intensity is somewhat consistent, is that ever, do you always want a clear sky to take not the optical measurement, or are there ever certain times where you can have like clear overcast?
You can always take.
Or perfectly distributed overcast, I don't know how to explain that.
No, so it's like, well, I'm from Oregon, so we get, you get that condition that you describe quite often. It's totally overcast. You look around in the sky and it's just thick clouds. You can't see any variation even in the cloud density structure there. So the answer to that is you can always make those measurements, but what happens in terms of trying to understand how to calculate Ks, it becomes, got a bright line, pushing a high intensity of light down in the water column. So it's sort of a signal to noise issue. We got a lot of signal coming into the water, a lot of light coming to the water. You have a radiometer, your measurement system that kind of measures some over a certain range. It's really bright, you're measuring right at the top of the range, and as you go down, it's starting to approach the noise floor of the instrument. Now in that same case where you started here and now you're starting here in terms of the incident light, you're closer to the noise floor. So at some point, that's part of it, you'll reach a limit faster basically to when you can't calculate Ks. Your Ks just become so noisy because you're right at the noise floor.
To my understanding, it's easier to subtract out a homogeneous sky than it is a patchy sky.
That is true. That is very true, but that's why we do that normalization here. All right, it's on the last figure. This is why we do that normalization. So you're sitting, typically you do this right above the sea surface. So you get out of that sea surface state. It's this in the next slides. So you're using that measurement to normalize by, well, it's going to see a cloud going over it, as well as the radiometer that's profiling. So you can match those two up in time and say, well, that one little dip I saw right here, when I look at my surface irradiance measurement, it's the same dip maybe not obviously in the magnitude, but you can see that frequency fluctuation. So that's where that normalization helps with, is to take out some effects on the sky conditions. Clouds coming by, those kinds of things. Yes, it's much better to have a beautiful day like today. It's perfect conditions. You don't have to really over process your data. This is great, especially when they see surfaces flat as can be. That doesn't happen very often, obviously. Been here almost 2 weeks, and I think this is the first day we've had it, right? So, okay. Well, I didn't talk about this too, but that's the other thing, and I think Sashi said the other thing you have to denote in the data submissions is bubbles. Where do bubbles come from? Well, wind can come over the top of waves, create these horsetails. So you get all these bubbles coming in and little droplets that have some air onto them coming in. Waves that actually break, induce bubble fields. What happens? What's the scattering of a bubble in water? Big? Small? Is that consensus there? Any?
I would say big.
Feels big.
It does, and why?
Because it's different fraction.
Correct. It's a huge difference in index refraction. It's the same, very similar to the same index of refraction difference between the air and the sea, which is big, 1 and 1.34. So the scattering effects, bubbles scatter really, really well. So obviously, that's another thing you want to note when you're out there. Am I seeing a lot of bubbles? Am I seeing a lot of white caps? Am I seeing a lot of horsetails? Actually, a lot of the processing algorithms, I think we're going to get to later, in terms of actually processing the satellite data, use wind speed and a component of wind speed, and basically affects the wind speed and where you can and can't use the data because the wind speed's too high and you're going to get a lot of bubbles, white caps. You're going to get a lot of surface reflectance, not much penetration or results of coming out of water ocean in terms of its radiance. Okay, so what about PAR? We talked about PAR yesterday, the definition of the PAR. Is it constant? Is K-PAR constant with that? Why? Why is it not constant with that?
It's not homogeneous. You have stuff at the surface and then it dies off, so you have different attenuation.
What type of attenuation though?
Um,
The clue, depth,
okay.
color of light.
Yes, so.
So you have absorption always going on by water. And that's not a flat function. So each of these wavelengths is getting attenuated more and more or less and less with depth at each of these spectral bands. So this is basically, I have to consider absorption and how absorption is removing light out of the light field. That's going to produce a different spectrum here versus here in irradiance. We saw all that. But PAR is an integration of all those bands. The total amount of irradiance coming out across the visible spectrum. The visible spectrum absorption impacts the irradiance distribution. So if I took a K-PAR here, and a K-PAR here, they're going to be very different. Because I'm integrating over the spectral domain. And I may not have any more, as you can see, any more red light down here. Where up here at the surface, I had red light. So you're spectrally attenuating more and more light down to whatever is the most prominent wavelengths of light that are getting through the water surface via the upper layers. Does that make sense? Same equation, but instead of doing it just at one waveband, we're doing it across the full spectrum. There's a lot of different models. Where you can use one KD value, but you have to know, and I think Hydrolight produces some of these too. You just have to know exactly what wavelength of light, and then obviously you have to define what the IOP conditions are. This is sort of a generalized model. Morale. So it's kind of generalizing over these conditions, case one waters, this is a generalized model. Where if you're only making KD at one wavelength 490, you can generalize it to IPAR.
What is it off?
I don't remember what the I is for. I don't know, Sasha or Kelsey, or do you remember what the I is for in IPAR in this generalized Morales model? Yeah. Imaginary. But that instantaneous, okay. Okay, so some pros and cons of K's. Pros are you're using one radiometer basically, unless you've got a surface radiometer as well, a radiant sensor or radiometer. But at least your profiling one is using that same radiometer through your whole depth profile. So if that radiometer isn't calibrated well, maybe it's off by 5%, 7%, you'd still make that K measurement because the theory is it's uncalibrated or not very well calibrated. It's going to have the same uncertainty in the instrument measurement all the way through your profile. But all we're looking at is the change derivative in that radiance or irradiance. So a bias or an offset drops out of that equation and is derivative. So that's the nice thing about it is you don't have to have a perfectly calibrated radiant sensor to do that, make that measurement. Now you can't use that measurement for an absolute value of irradiance because it's got a high uncertainty in it, or it's uncalibrated or not very well calibrated.
Could you use digital count directly output from the instrument before any calibration
To do what?
to compute the K?
Not necessarily depends on the type of radiometer, I guess. Some use linear amplifiers with changing gains settings. And some of them automatically adjust those to try to get like 7 to 10 orders of magnitude in irradiance measurements. So digital counts, you always have to correct them for whatever the integration time is, how long I'm actually viewing, making that measurement and filling up my spectrometer or filling up photodiode. So you have to know if it's a linear amplifier or a linear detector system, or it's a log linear. So you have to be careful in just going right to counts without accounting for if there's changes in the integration time. So if I go from 40 millisecond integration to 100 millisecond integration, I still have the same range in counts, but I have to correct for that difference because we've switched to a higher or lower gain setting. That makes sense. All right. Radiative transfer theory provides connections between these Ks and the IOPs and other IOPs, AOPs as well. So you saw some of that yesterday, at least. Direct one, remote sensing reflectance. We'll get to this. It's equal to the G over B back over A plus B back. Well, we'll get to that. I'll show you the equation in radiance, in irradiance space, how to do that same measurement for remote sensing reflectance. So the point is there are these connections through the AOPs in radiative transfer theory that help us drive radiometric measurements, use radiometric measurements to derive IOPs. And vice versa, actually. That's what we did yesterday, it's vice versa. Use the IOPs, give me some AOP, or even the irradiance or radiance fields. Great other thing about it is about 90% of the water leaving radiance, which is what's coming out of the ocean, about 90% of it comes at a depth, from a depth of 1 over the KD value. Another way to interpret this is why remote sensing is really good. So you have a really low AV value. You have a very deep penetration depth, meaning I still get a lot of light from very deep waters that comes out of the ocean. That's the cool thing about this in terms of remote sensing reflectance and satellites. You get a depth view of it, but as you learn, put more stuff in the water, shallower depths you're going to see because I got more absorption going on. If you've got a lot of chlorophyll particles, things like that. CDON. Cons. These really aren't that constant with depth. Even in homogeneous cases, sometimes they're just not constant with depth all the time. We saw that in that example of K-PAR. Still got homogeneous waters, but the whole spectrum is still changing in K because you're getting more and more absorption and loss of those different spectral bands. The other good thing is the greatest variation is in the near surface, but there is still some dependence on the light. We saw that wave focusing, those kinds of effects. But most of, the particles and things are in the upper surface, and that's what we want to really measure is what is the surface ocean doing in terms of growth patterns of phytoplankton. However, it can be difficult to compute derivatives with very noisy data. Again, if you go back to that very noisy spectrum that I showed, really hard to pick which 2 points you want to calculate because it's going back and forth, back and forth. You have to do a fitting function to those variations to extrapolate it back to the surface. All right, here's another AOP called the average mean cosine. These are the definitions. If you think back to the definition, this is the irradiance, and the planar irradiance in the downwelling divided by the scalar irradiance in the downwelling. You can do the same thing for the upwelling. You can do the same thing for what's called the average cosine, which is the planar irradiance divided by the scalar irradiance. So remember what this is?
Yeah.
No, sorry, this parameter.
Easy.
Vector irradiance.
Correct, the vector irradiance. And this is just EO. So if you work out all that math, what you'll find is essentially what we're measuring is this cosine angle. So imagine straight down this vector here. That cosine angle is 0. Cosine of 0 is 1. So it's a high value when all the light is going in one direction straight down, perpendicular to the sea surface. But as you get more and more spread in that function, it's the cosine of that. So you're getting more and more different light field positions. And if they're equal in every direction, here, that cosine average is now 0. Everything's going in the same direction, or equally in the same direction. All different directions, all different directions, all the light field, all the irradiance is propagating the same everywhere. So this is very close to the asymptotic state. Yes.
Is this like used to look at like sea state and stuff, something like that? I'm trying to figure out like a metaphor in my head.
Why you'd want to make this measurement?
Yeah.
Get to that in a second. Yeah. It's another interesting component that you can drive again an IOP from. It's one of the parameters you need to drive another AOP from. So the idea is here is what you're looking at. So if you got a sun zenith angle that's coming in, it's not 0, it's not straight down, it comes in. as we saw in the plots I showed you in that same depth of the fisheye camera, you could see a little bright spot. That's where the sun is. But now as this, you take this, that angle's now over here. Now you've got this angle that changes. The average cosine changes. It's saying, oh, kind of more, you know, if it was clear skies, the sun might be over here at this angle. Of course, you have to get it through the air sea surface, do that transformation, all that stuff. That's the Good. Okay, so what do they tell us? Again, if we look at this and you think about the plots you did, varying scattering components, varying absorption components, right? So what happens when you get a lot of scattering?
The light field becomes diffuse quicker.
Correct. What happens when you get a lot of absorption?
Light extends faster.
Pardon?
The light extends faster.
Yes. Exactly. It's getting absorbed faster, it's attenuating faster, right? So here's the whole thing. AOPs are closely linked together and can be used in an inverse problem. More on that right now, not later, sorry. But essentially, KD, kind of a good approximation, pretty darn good approximation of A plus D back over the cosine of that angle. The average cosine angle, which is U bar. So you can use KD measurements if you know what the average cosine is to get at A and B back. Or A plus B back. Typically, it's most commonly assumed, you know, this measure more better approximation of A than B, but that's not totally true in very high minergenic concentrations. As you saw in some of that modeling, now the scattering becomes a really big dominant component of your IOPs. So your albedo is getting brighter and brighter and brighter. There are some ways to model this average cosine. There's plenty of other references I can give on this, plenty of ways to sort of model or guess at what it would be. This is just one of them. So, where J is cosine of theta. Okay, so another set of AOPs or reflectances, what you've been measuring. All are in some form of upweld light normalized by downweld light. That's kind of that reference, how much light's leaving the ocean over how much light's hitting the ocean. So what does the satellite measure again? It's measuring a whole bunch of things. Boundary effects, surface reflectance, some of that light's getting into the water, some of it's getting scattered back out of the water, hitting our spectrometer on our satellite. Some of it's doing the same sort of thing in the atmosphere as well. So typically we measure radiance, which is what a spectrometer on an ocean color satellite is measuring. It's not measuring irradiance, it's measuring radiance. It's got a little cone on it. It's got its paper towel on front of its optics. But we typically don't want to measure straight down. Various different reasons for that, but mainly it's to avoid sun glint. Sun glint is very strong when you're looking straight down or at some angle. So we usually typically tilt the sensor to look at an angle relative to the sea surface. Typically in a satellite, we normalize by a model of plane irradiance. This is called normalized irradiant remote sensing reflectance, but you've got to do that normalization in the bottom part of it. It's often further normalized to nadir view at sun and at nadir, so you always have to account for. I think you're gonna get more into this later this week or in the next lecture, but you've got to account for, as we talked about in the radiative transfer, where's your sun, where's your light source, how's it hitting the earth? At what direction is the light coming out of the ocean that I'm measuring it? So you always have to account and say, what is this angle? That's getting into the sense you're seeing. Well, that depends totally on also the sun angle. So remote sensing reflectance, again, just a reminder. Generalized form we've been working with. Here's the definition in radiometric terms. So you've got a measurement called water leaving rate, which is measured in air at some theta phi angle and some wavelength. You divide that by the downgoing irradiance, typically in air. You'll also see this in literature a lot. Instead of calling it AD, they call it ES, surface. I know everybody likes to have more and more little symbols, but for me, it always helps if I see an ED measurement. I assume, but always double check, it's in water measurement. When I see an ES measurement, I assume it's above the surface of the ocean. Okay. This is the fundamental quantity used in ocean color remote sensing again. What we typically do here is measure the upweld radiance at the sensor. Some of that's due to the atmosphere, some of that's due to the reflectance of the sea surface, some of that's due to actually the water leaving radiance. So you have to really do remote sensing, you have to correct this for all those different components to derive LW. ED, typically, or at least I think the best way, is we measure, because there's great models of how much irradiance is hitting the Earth's top of the atmosphere. Lots of models, very awesome models that have been developed to account for solar sphere changes, to account for Earth sun distances, all these kinds of things. So you're driving a parameter and doing the normalization, what the satellite's measuring at the top of the atmosphere. That helps us get rid of all that, what's going on through the atmosphere and how much light's getting attenuated and scattered. We just normalize it by the top of the atmosphere. Many ways to do that, but again, the whole point is remote sensing, you're trying to get this number. So I like it because it makes this bottom normalization parameter a very low uncertainty versus trying to make a measurement down at the surface and now propagating it through the atmosphere, which now you've got all these correction factors you got to do for what the atmosphere looks like. So, okay. RF shows almost a dependence on the sky condition and strong dependence on the IOPs. We'll get to that. So it's a very good AOP. So what is water leaving radiance? So here's the pictogram, sun shining in, hitting point, getting into the ocean. Some of that light is reflected. Some of that comes off at some angle that a sensor might see. It's the same angle. It's blinked, reflects it off the ocean. Some of it comes out of the ocean at that same angle Blint is at. So what you're trying to derive is this measurement based on in situ or just above the water. We'll get to the measurement techniques. So if we have profiles of LW in the water, we can extrapolate that to just below the sea surface. So it's 0 minus, it's called. Get that very just right below the sea surface. Now we have to transmit it through the air-sea interface. We've got to correct for the air-sea transmission. If we have above water sea surface measurements of LW, we must remove this reflectance factor. Because what you're measuring really is L total, which is, and doing it from above, which is the reflectance off the sea, plus the water leaving radiance. Okay. So just a reminder, This is some examples here. I put it as ES again to say it's above water. This is spectral plot, just relative downwelling irradiance here. Here's the irradiance at the surface. Here's the irradiance in red. Here, irradiance in red. So we're trying to get at that ratio. LW or LW over ES. In this case, I'm just plotting LW over LU. And correct it for the RC surface. But we're trying to use this measurement, normalized by that measurement, to derive an IOP. Other thing, I put this up here as a reminder. It really depends on your spectral wavelength resolution. If you got 10 nanometers, you want to just run a smoothing filter over this and 10 nanometer bandwidth. Little bumps and wiggles here are part of that interpolation. So they do impart small factors in your smooth spectrum. Does anybody remember what these things are? The cause of these little things are? Well, Fraunhofer lines, so that's Fraunhofer lines are the absorption by different molecular species in the photosphere, solar sphere. And then there also can be caused by absorption of gases, same kind of gases, molecular gases in the atmosphere. So these are very sharp absorption peaks in both the output of the sun and what's in the atmosphere. But the great thing about these is that they're pretty constant. You always know where they are spectrally. They're based on a molecular property of the molecule you're looking at. So they're really, really great at saying, how close am I actually measuring this peak? Am I off by half nanometer, 1 nanometer? Really good ways to spectrally calibrate your instrument. But you have to have a really less than 1, ideally, spectral resolution radiometer to really resolve them. But you can see them even at 2 nanometers pretty well. Yes.
As human activity continues to put atmospheric gas or change the composition of our atmosphere, will these lines deepen or widen and we have to like reaccount those later?
Yeah, kind of depends on what they are. I mean, that's just like anything else we saw. If you have the same type of CDOM coming in and out, and you're just changing the concentration, it changes the absorption value. Same thing here. If you change those gases, the concentration of those gases, they're going to move. Yeah.
So would this spectrum look different if you were in like downtown Los Angeles versus like Montana?
Those are more different species more. I mean, you get some more CO2, but you're also getting a lot more aerosols, particle-borne stuff. And so that tends, those aerosols just are like eminerogenic, just kind of similar to that. They're just going to scatter everything. So it's sort of this combined effect of the two things. This is more like ozone, what we're talking about. So theoretically, you would see a different shift, and I don't remember where ozone, which line this is in ozone, but theoretically, if you were to go over, the Arctic, Antarctic region and over the middle of the ocean, you'd see that change. Yes.
Just about the reflectance. In one of the case, in general, we saw the term remote sense reflectance. But in land, in general, you saw like a surface reflectance. Do you know what is the difference of this terminology?
Land versus ocean?
Yes.
Oof. There is good generalizations. It depends a lot on what the type of material on the land is. Think about it, energetics are coming off sands, usually much brighter, higher albedo than tree laden parts. You got a lot of absorption going. So relative to the ocean, I mean, land reflecting huge relative to the ocean. I mean, much, much greater. But orders of magnitude, great. This is another effect that we have in terms of remote sensing is as that satellite's now going across a very small valley coming out of the ocean. And it hits Saharan desert. Boom, all of a sudden you got this ginormous signal coming up. And it takes the spectrometer a while to sort of do that adjustment going from land to the ocean, ocean to the land. So this is another parameter you'll learn about in remote sensing. That's why these boundaries between the land and the ocean are often flagged or even removed, because there's this land adjacency effect. Sort of it's like your eyes, you stare at the sun and you look back down at the ground and you're like, oh, I can see. It's very similar to that. But on a satellite that's moving very rapidly, that little burn over time is really, really tiny, tiny short. But the satellites just scream along over the top of the Earth. Okay, so let's get into the measurement techniques. One of the first common ones, this is from a system called MOBI. That's off of the island of Lanai, Hawaii. It's been there, how many years now? 20 plus years?
20 plus for sure.
Yep. So it's a mooring, the deep water mooring out off Lanai. Surface buoy, we're looking down on it. It has these arms, a set of 3 arms that come off this buoy, each of which have radiometers on them. So they're all at fixed depths. It's also on the top of the buoy an ES sensor as well, but there's 3 fixed depths. So now you have 3 points over which to calculate K. Derivatives from, you can do it from 1 to 2, 1 to 3, 2 to 3, all kinds of things you can look at there.
Why is putting radians at the 2 different depths multiplied by the downwelling radians above the surface in the computation of the LU?
Oh.
Sorry.
No. Oh,
We love it when you challenge us.
pardon?
You're saying we love it when they challenge us.
I do too. This isn't the best derivation.
Because because I knew and there was radiometric at 6 depths and I never did that. So I'm just wondering if I do something wrong or
In terms of the
yeah.
0 plus is what you're talking about. That shouldn't be 0 plus. It should be Z basically. Z1, Z2 here.
But no, I'm confused by the fact that KLU would just be like the derivative of LU alone. I'm wondering why downwelling radiance above the surface is entering this. Is that some kind of normalization for the downwelling radiance above the surface? I don't understand why it's entering here.
Oh, I don't either now. I didn't catch this.
Normally.
Oh, okay.
No, it is normal. Yeah.
Okay.
Yeah. It's a normalization. Let me correct that now. When I post this up, I'll put the better definition there, but you're gonna see it repeated all the time because I cut and pasted this. But thanks for pointing that out. Okay, so any questions on that one? So this again, you've got your irradiance sensor here, downwelling irradiance at 0 plus, and then you've got upwell radiance at very different depths, and you're just calculating. You have to be able to propagate that light from these 2 different depths. You derive a K in order to calculate what L0 is minus it.
We have already said, what type of sensor is movie, or is?
Say that again.
What type of instrument is movie on?
There's LUs and EDs on them. So both. One measuring downwelling irradiance, one measure upwell irradiance. So 2 on each arm.
I'm a touch confused about the formation of the radiometers and how it seems like they'd be, at least in the diagram, they're like getting shorter and shorter close to the stand, right?
Yeah,
It looks like it would be like self-shading maybe by the upper sensors, like in my head, I would think like they get shortest and then expand out.
it's harder to show this, but they're all rotated. So you got one on this way, you go down, it's another one with no.
Okay, that.
Yeah.
Answers that, but I was confused though.
Yeah, they're not all directly below each other, but then basically you're trying to get out of the shading of the buoy.
Yeah.
What really you're trying to get out of, and that shading does affect the lower ones as well, but by that time you're.
So it's the same sensor, they're just pointing the different directions.
Yes,
Okay.
not the same sensor.
Or, oh,
One's irradiance, downwelling irradiance, one's upwelling radiance. Yep,
I found the paper from 1997 talking about movies, so I think we're looking at 30 years now. So,
there you go.
yeah, like time flies when you're having fun.
Yeah.
Yeah. Older than anybody is probably the audience.
And this data, actually, you can get all this data is all online as well. So the whole history of data is online. Typically, I think they measure it 3 times a day,
Yeah, I think so.
something like that, 3 times a day. So you get 3-time realizations. Typically,
Your calibration.
yeah, typically they try to match it to when the satellite is actually going to overpass as close as possible in time. Measurement.
What's T sub F and why is that? Why is LWN equal to 0.543?
So this is the air sea reflectance. Transmission through the ocean divided by the square of the water. So it's just basically the transmission function to correct for that air sea difference. Both in index of refractant change and in the transmission through the air sea.
So T sub F is not wavelength dependent, or it is wavelength dependent?
You have to look up what these are. I mean, index of refraction of water. It's pretty consistent.
There is a small spectral dependence, but it's really.
It's very, very small.
The
Yeah.
paper by Voss and Flora 2017 on the
Yeah.
operation.
And why is LWN equal to a constant?
That's not equal to a constant either. Well, it's dependent time dependent.
Oh, is that 0.543 equal to TF over NW squared?
Yes, sorry. I should be more space here.
Maybe comma.
Yes, or a comma. Comma. 0.543. So that's just an easy, quick approximation you can use. So if you get to this measurement right below the water, LW, you can multiply it with this number, LW. So you get LU right below the sea surface.
Gotcha.
If you multiply it by 0.543, you can derive an estimate of LW. There is a slight dependence on that wavelength.
Just above the water, it's index. Easy to go precise about the.
So the point is, we're trying to get to here. We've got 3 depth dependent measurements of LW and ES or ED. You need to drive Ks, KU or KD in order to take that light at whatever depth you want to use and propagate it up to the sea surface. So that's another always way, and Moby does this quite frequently. They got 3 different depths. They can calculate 1, 2, 3, 4 different Ks. Use those Ks to drive what that LW is. Do they really converge it or are they way off? That's usually one of the QA/QC parameters. It's my LW calculated using different Ks from those 3 different depths. Do they all converge? Sorry, she had a
Is
question.
this sensor I assume would be most useful in like waters where there's not much variation in the optical properties
Correct.
between all those depths? Like if you had really high chlorophyll variance across these 9
Correct.
meters.
We-
Messy.
It's not really it's case 1 waters, but it's the super case 1 waters where
Okay.
chlorophyll is almost non-existent at the lowest possible, where the waters are very, very homogeneous, way down well past the penetration depth of the satellite. And there isn't a whole lot of variation, like I said, in the IOPs. So typically, this is why it's off Lanai, Hawaii. You're trying to pick a space where it's beautiful. And it doesn't vary much, and the ocean always looks beautiful. So there are some sites in the world that do this. Hawaii is one of them. Around a lot of the Haitian islands, a lot of the other islands that are out in the middle of the ocean. Those are very clear, very consistent absorption property or IOP properties in the water. So you're right, you can do it in sites where there's varying conditions. But if you're trying to calibrate an instrument, your satellite, you want to have a very, very solid condition in terms of the IOPs. You're going into my talk on Friday, which is a great question. Sorry, you had another one.
Yeah, I just found what is this term. It's if the LU at Z1 and LU at Z2 are not acquired at the same time, the EP0 plus term is used to normalize for the change in downwelling radiance between time 1 and time 2.
Ah,
So like
Right.
cloud houses over.
Yeah, but in the case of
It is the
continuous
normalization.
measurement, like at fixed depths, so this would be more used in profiling, but in fixed depths, we wouldn't need to normalize because it's simultaneous.
you're right.
That's
Thanks for
why I was
looking up.
confused.
I couldn't think of that. Thank you for looking that up. Yeah, these are two different times. You have to normalize that by those two different times, because when Moby was created, yeah, they're not all measuring instantaneously. It's kind of one really in time.
They're not measuring instantaneously?
They do now. I think in the original incarnation, they did, yeah. All right, so let's go into underwater profiling. This is another way to do it. Here's all those same credit equations, again, confusing as heck. No comma. So this is a case where you're still making an ES measurement above the water. You're going to do the normalization, but now you have a radiometer that just profiles slowly down through the water surface or rapidly, depends on how fast and what resolution you're trying to get at, depth resolution you're trying to get at. Slower you go, the more points, the more depth resolution you have, faster you go, the less depth resolution you have, and you're also kind of smearing out some of like the high frequency effects. That's right. So various examples of this. Here's a ED, there's an LU sensor, HyperPro, which we'll use in the lab, same kind of configuration. You got an ED and an LU. The system that I work with, do the PACE held out. I only have two LUs, two independent LUs, and this is just to use a relative measurement of both, basically, so I can get an error function between the two different systems. I don't do an E, I do an ED measurement here, but it's only 4 channels. We use models to basically estimate what the E at the surface value is. So we use these radiative transfer models to derive those. All right, my buddy Emmanuel. Moving off the island of Crete, swimming gently and calmly with a hyperhand system. So another way to do this is just purely from above water measurement. So I'm trying to do what we talked about before. Is the light impinging on the surface of the ocean? Is the light coming out of the ocean? W, some of that light's getting reflected. And then we put a radiant sensor that's staring at the ocean at some angle. We also put a radiometer that stares up at the sky at some angle. Same angle here, basically. 1 degree this way matches 1 degree that way. And then you've got your downwelling radiant sensor. So typically, if you look at Fresnel reflectance coefficients versus nadir angle, you rotated that, what that coefficient could be around the azimuth. What you see is about 40 degrees viewing nadir angle. So that 40 degrees here, 40 degrees here is where all this variation kind of collapses very cleanly between all the different azimuth angles. And if you look at that azimuth angle where they converge is 135 degrees. So we're trying to find a spot and these different view angles where we're less dependent on where the sun and sky is and what the actual view angle is. So you'll see that in today's lab. This is the system we're gonna do in the lab. Here's your LW measurement. But it actually includes an LT measurement. So it's the reflected light plus the LW light that's coming out of the ocean. And then you've got your sky or your radiance coming off through the atmosphere from the sun. And then at the top, we've got irradiance coming down. Another system, another example of another system. So you can imagine yourself on a boat, sailing around, you got to go around islands and stuff. And find you constrain it to 40-degree nadir view angle, 135-degree relative to the sun's azimuth angle. Well, you're both steering and moving. So these two systems are set up, and you'll see them, they're pretty cool. As the boat starts to move, they keep that always that 40-degree angle. That's always set, but it always rotates around the azimuth to try to keep it within 135 degrees relative to the sun.
When we use this pattern, we for example, correct the energy effect because the sensor is fixed in a specific angle.
Yeah.
And when I use this data, I need to correct it.
Yes. You need to correct it back for a 0-degree angle, or vice versa. If you're making a 0-degree angle, like on a profiling instrument, you need to correct it if you want to get it into a relationship to what the satellite measure. You have to do all that correction, which I'm not going to go through here today. There is a way, very complicated way, F over Q, to try to correct for all that viewing geometry. All right. So that's the above water. The other way to do this, and we have this in the lab, is have a buoy that sits right at the surface. And we make one measurement of ES. There's ES, it's right above the surface. There's an LU measurement. It's just below the sea surface. So that's the concept. We're really after remote sensing reflectance. So why don't we just measure right at the sea surface? Well, again, go back to what I said here. Where did I go? You still got some component of the sky reflectance coming in. Your LW is just above this water surface. Sorry, I said in water, but it's just the LU is for actually right above the sea surface. So you're trying to measure without having to do all these transmissions through the air sea surface. Trying to measure ES above, LW right below, right above the sea surface. But again, as I went back, you still have this surface reflectance part of it. So various people, John Ping Lee and others decided, well, why don't we just put a cone on this thing? Goes into the water, so we block the sky. LR is gone. So this is called the sky block method. It's another way to do this. All right. I think I'm going to jump into the uncertainties here. So we went over all these 4 different methods. I'll note that these ones pretty much, these two have the same different types of uncertainty. You have some uncertainty in the actual radiometric measurement. Is it calibrated well? What's its thermal effects on the measurement? Is the system heating up? You both have to do a vertical extrapolation. Both have tilt problems doing this. So now you're changing your theta value as you move around. Even a buoy that sits in the sea surface is going to rock with the waves. So all these things are swinging back and forth. Fouling, not so much with a profiling one, because you can pull it out and clean it after every profile if you want to. Definitely, these things are out constantly, rotated out, I think every 6 months or so, but they go out every month and use toothbrushes, dive and clean it. Depth, you have to be able to measure depth really well. So this is also bobbing up and down with the waves. So where's your actual depth relative to the average sea surface? You gotta do that correction. Same thing here. You got a really rough, trying to measure at a 0.5 nanometer or 0.5 meter scale, and your depth sensor is only good to 1 meter. You've got 0.5 meter uncertainty right there. Transmittance through the air sea surface, we talked about that, there's some air there, and unstable illumination, clouds, all this stuff. All kind of been part onto it. Above water, you have to remember the radiometer, uncertainty, the reflected skylight, tilt, shading, fouling, unstable illumination. And this is what you talked about, those little bits called by reflectance function, basically, with the RDF, where you have to calculate and know where everything is in terms of all your angles. And what that condition looks like underwater. And here you also have some atmospheric path issues you have to deal with if you're looking at these angles here, and you can do that. Sky block, that's the nice thing about that, it kind of reduces down to just a handful of things. All right. I think that's it.